In this module we will talk about basic circuits and their mode of connections. We will dive into topics such as series and parallel connection. Technology is the main driver of our society. As you may know, the current developments is basically a leap from a primitive technology such as communication. These advancements could not occur without integrated circuits that has increased the speed of computers while reducing their sizes. All of these occurred in less than 100 years. In this module we will dive into understanding the basic structure of integrated circuits. What is an electronic circuit? Wikipedia defines an electronic circuit as composed of individual electronic components, such as resistors, transistors, capacitors, inductors, and diodes, connected by conductive wires or traces through which electric current can flow. The figure shows a basic circuit containing a light bulb, and we see the flow of electrons from a battery source. The electrons are pushed from the negative side of the battery and it is pushed towards the light bulb and we see it illuminate. We see that when the loop is cut off, the flow of electrons ceases and the bulb no longer illuminates. Here the bulb acts as a resistor where the flow of current induces illumination and heat, thus generating light and heat energy. The wires here act as conductive material that transmits electron flow from the battery source. The battery here is the one that pushes the electrons to migrate due to electric potential difference or voltage difference in the battery. We can think of batteries as a water tank that stores energy and pushes water out of the tank. As the stored water is reduced, its pressure is also decreasing, and we can imagine this as the electric potential or voltage decreasing. When an electron flows from one point to another, the rate of flow is called a current or electric current. Symbol is capital letter I with units called ampere or letter A. In a conducting wire we have electrons about 1 coulomb flowing and a pure laminar flow or unobstructed. The rate of flow of charges for 1 coulomb worth of charges over 1 second is given as I equals 1 ampere as shown in equation 1. In reality, conductors, or even good conductors, have resistance and the path is not a straight path or unobstructed as shown in the figure. In conductors where the atoms are arranged in a grid-like pattern, the electrons would collide with them and distort their path. The collision occurring inside a conductor produces a resistance. We label resistance as capital R and its units are called ohms. The motion of the charges in the presence of electric fields and these obstructions will slow down or drift. We call this motion drift velocity, which is defined as the net ratio of the net displacement over time. The direction of the electron is going in the opposite direction as the electric field. The force exerted on charge will be an attractive force. Earlier literature used protons instead of electrons in terms of flow of charges, but now we know it's the electrons or free electrons that actually move from one atom to another. Whether electron or proton flow is used, the current is going in the same direction as the electric field, and this is called conventional current. Current density denoted by J is the amount of charges in a volume. Here we have charges moving across a wire with a surface area A and these charges moving at drift velocity. We take a small area with length dx and measure the amount of charges passing through that area. The volume of the slice is given as a function of the length dx times the area as shown in equation 3. The number of particles of electrons passing through the thin volume is given in equation 4. If each particle has a charge q, then the amount of charges is given as in equation 5. The current expression in equation 1 can be expressed as equation 6. Current density in terms of current is expressed as the current of electrons passing through over a cross-sectional area A. We write the function as in equation 7 where the area cancels out. We notice that J is affected by the size of the wire in the sense that it is inversely proportional to the cross-section. Large wires will have smaller current density than a smaller wire. Equation 7, which shows the proportionality of the current density and electric field in the equation, is called the Ohm's law, discovered by the German physicist George Simon Ohm. Ohm's law is an idealized model that describes the behavior of some materials, but it is not a general description of all matter. Non-ohmic conductors have resistances that vary with changing current, voltage and temperature. Non-ohmic conductors have resistances that increase with temperature, such as semiconductors, which we will discuss a bit later. Current density can be written as a vector quantity as shown in equation 8. The charge q is left without any absolute function, so that means that the polarity of the charges will alter the direction of the current density. So when it is a negative charge, current density moves in the opposite direction with respect to the electric field. Sample problem. An 18-gauge copper wire with a diameter of 1.02 mm, carries a constant current of 1.67 A to a 200 W lamp. The free electron density in the wire is 8.5 x 1028 per cubic meter. Find the letter A, the current density, and letter B, the drift speed. For letter A, we recall the equation for the current density, which is given in equation 7. Here we see that we need to determine the area of this wire, so we solve this by using the area of a circle. We then substitute it back into the equation for the current density and we get the value here. For letter B, to determine the drift velocity of the particles, we use equation 7. Rewriting this equation to solve for the drift velocity. We then get the number of charges using the free electron density, and the charge is just the electron charge. So after substituting the values obtained earlier, we have the drift velocity shown here. Current density is affected by the type of material being used and the presence of electric fields. Shown in equation 9 is the relationship between current density and electric field, and we see that they are directly proportional. The symbol ρ is the material property called resistivity with units of ohm meter. Shown on the table are different materials' resistivities at room temperature. We see that conductors have very low resistivity, which makes them ideal for conducting electricity and heat. Insulators show very high resistivities, which makes them ideal for preventing flow of electricity. The reason for the A useful way to visualize the difference between conductors, insulators, and semiconductors is to look at the difference in the distance between their valence bands. You may recall your chemistry about electrons about these things. The theory that studies deep into the behavior of materials' conductivity is called band theory of solids. The band here refers to the energy band gap, which is basically the space between the valence band where the electrons reside and that is closer to the atom, and the conduction band that is the farthest shell from the atom. So we see that for metals the conduction in blue and the valence band in red are overlapping, and this allows the free movement of electrons. For the insulator we see that there is a large gap between them and hinders the flow of electrons. The material in between is the semiconductor, which has a tiny gap and which allows some electrons to flow. Semiconductors are the most interesting material to work with, since it allows engineers to develop different devices such as computers. Conductivity is just the inverse relation of resistivity, and here we denote it as a symbol sigma with units the inverse of ohm meter as shown in the equation here. The resistivity of a metallic conductor increases with increasing temperature. As the temperature increases, the ions in the material vibrate, thus increasing the collisions between electrons and atoms. The increase in collision impedes the motion of the electrons, which reduces its drift velocity. Equation 11 shows the relationship of resistivity and temperature. The temperature T0 is the reference temperature, which is usually set as 0 degrees or 20 degrees Celsius. The factor alpha is called the temperature coefficient of resistivity with units in per degrees Celsius. The graph here shows the trend of behavior of resistivity when the temperature increases. The coefficient of resistivity varies with the type of material as shown here in the table. Semiconductors behave differently when the temperature increases. A nonmetal graphite will decrease in its resistivity when temperature is increased. We see here in the graph a model for semiconductors. Suppose our conductor is a wire with uniform cross-sectional area A and length L. Let V be the potential difference between the ends of the conductor. The conductor is connected to a battery, so it will have a high potential end and low potential end. The current will be pointed from the high potential to the low potential, which is the direction of the electric field. As the current flows, the potential difference, the potential energy decreases, and the energy is gained by the atoms in the conducting material during collisions. Here we assume that the conductor has consistency in its material's physical properties, such as cross-sectional area and arrangement of atoms. This results in the current density and electric field to be uniform throughout the conductor. We recall the expression for the electric potential difference in relation to the electric field, which is given equation 12. We manipulate this together with equation 7 and equation 9 to arrive at an expression for the electric potential V. We equate equations 7 and 9 and then substitute the expression in equation 12, and we arrive at a function for the electric potential shown in equation 13. The equation shows the relationship between the current and voltage, and they are directly proportional with each other. We see that the factors in the parameters on the same side as the current are constants or assumed constants, and they are the area, length, and the resistivity of a conductor, which we call the resistance of the material, which we write as R and as an expression shown in equation 14. Equation 13 is now written as equation 15, which is also known as Ohm's law. Using a water tank as an analogy to resistance behavior in a conductor, the equation shows that the resistance is inversely proportional to the cross-sectional area. So, the larger the cross-sectional area, the lower the resistance. The equation also shows that resistance is directly proportional to the length of a wire. So the longer the wire, the greater the resistance. This behavior is due to the atomic arrangement and condition inside the conducting material, which impedes the flow of electrons. Resistance of material is also affected by temperature like resistivity, and it is expressed in equation 16 with R0 as the reference resistance at T0. When the size of the conductor, the length, and cross-sectional area is constant, the resistance would not be affected by the change in temperature. This is due to the behavior of its atomic structure inside the conductor. Resistors are circuit devices used in electronics that exhibit ohmic behavior. The figure here shows how to calculate its value. The color on the resistor indicates a certain value of its numerical digits, multiplier, and tolerance. This figure shows the forecurve of an ohmic material which exhibits a linear behavior with the slope being the inverse of the resistance. The graphical representation of a resistor is shown as a zigzag line. Here we have, an 18-gauge copper wire has a cross-sectional area of 8.2 times 10 to the power of -7 meters squared. It carries a current of 1.67 amperes. Find the electric field magnitude of the wire, potential difference between 2 points in the wire 50 meters apart, and resistance of a 50 meters length wire. For letter A, to determine the electric field magnitude of the wire we use the equations 7 and 9. Rewriting it to solve for electric fields, and we see we need the resistivity for copper. Substituting the values we have, the magnitude of the electric field is about 0.035 volt per meter. For letter B, to solve for the potential difference between 2 points in the wire 50 m apart, we use the equation 12. Substituting the values obtained earlier and the given, we have the value of about 1.75 volts. For letter C, to solve for the resistance of the 50 meters wire, we use the equation 15. The resistance is about 1.05 ohms. Sample problem. Suppose the resistance of the copper is 1.05 ohms at 20 degrees Celsius. Find the resistance at 0 degrees and 100 degrees Celsius. The temperature coefficient of resistivity for copper is alpha equals 0.00393 per degree Celsius. To solve for the resistance of the copper at varied temperatures, we use the equation 16. The resistance at 0 degrees Celsius is about 0.97 ohms. And its resistance at 100 degrees Celsius is about 1.38 ohms. We see that as the temperature is increased, the resistance increases. For a steady flow of current, it is important that it is connected to some source and in a closed loop or complete circuit, otherwise the flow of charges would be zero. When a conductor is not part of a circuit but there is an initial flow of current, it produces accumulation of charges at both ends. The accumulated charges create an electric field that is opposite the initial electric field. The current and current density is reduced due to the presence of this counter-electric field. Eventually the magnitude of the electric fields will become equal, which results in zero current and zero current density. There will be no more flow of charges. So for a steady flow of current, it must be important that it is connected to a source of power such as batteries. Here we have a complete circuit where a resistor is connected to a battery as shown in the figure. Here we have a charge Q moving around a complete circuit. When the charge moves around the circuit, there is a decrease in potential energy due to the material's resistance. The loss of electric potential energy is due to the collision with atoms inside, and this typically generates heat. What keeps the charges in motion is the presence of the battery that pushes the charge from a low electric potential back to a high electric potential. Electromotive force, or EMF with a symbol, is an energy per unit charge quantity that acts like an electric potential. Interestingly, it is not a force, the name is a misnomer. Its unit is in voltage, which is the same as electric potential or voltage. EMF is not an electric potential, since electric potential is the difference measured between 2 points. EMF pushes the current flow to move from lower to higher potential as shown here in the figure. The battery here acts as a source of EMF. An ideal EMF source would be able to maintain a constant electric potential difference, and it is then equated to electric potential difference shown in equation 17. Here we have a battery having potential difference with point A as the higher potential end and point B as the lower potential end. The charge here is a positive charge, so it goes in the same direction as the electric field, so it is moving towards the lower potential. The charge experiences an attractive force as it is drawn towards the negative end. The source also produces a non-electrostatic force which pushes against the electric force. This pushes the charge to move from a lower potential to a higher potential. This is like pushing against the flow of direction. When the electric force is greater than the non-electrostatic force, the motion moves the positive charge from a high potential to a low potential. When the electric force is less than the non-electrostatic force, the motion moves the positive charge from a lower potential to a high potential. When the electric force is equal to the non-electrostatic force, then there is no net motion, and this occurs when the EMF source is not connected. The non-electrostatic force is the force that keeps the potential difference in a battery. The absence of this force would simply deplete it to zero potential. This non-electrostatic force depends on the type of source. Generators, which is an EMF source, the force is generated due to magnetic field force. In a battery or fuel cell, it is associated with the diffusion processes and varying electrolyte concentrations resulting from chemical reactions. Electrostatic machines such as Van de Graaff generators are due to mechanical moving belts. If a positive charge Q is moved from B to A inside the source, the non-electrostatic force does a positive amount of work on the charge, and it is given in equation 18. The amount of potential energy is associated with this charge equal to equation 19. The ideal source of EMF is where the electrostatic force and non-electrostatic force are equal in magnitude but opposite in direction, so the total work done is zero. So equating the work equations as shown in equation 20. The figure shows the EMF source connected, creating a closed circuit. The potential difference in the source creates an electric field in the wire, and this causes the current to flow around a loop from point A to point B. The potential difference is given as in equation 17. When a positive charge Q flows around the circuit, the potential EMF rises as it passes through the battery is numerically equal to the potential drop as it passes through the remainder of the circuit. Real sources of EMF have internal resistance denoted by small r and causes the difference in the potential difference and EMF not equal. This internal resistance still follows an ohmic behavior, so we can write the electric potential difference as shown in equation 20. We can rewrite this equation in terms of the current as shown in equation 21. Here we have a figure showing a source with EMF equals to 12 volts and internal resistance R equals 2 ohms. For comparison, the internal resistance of a commercial 12-volt lead storage battery is only a few thousandths of an ohm. The wires to the left and to the right of the ammeter are not connected to anything. Find the respective readings, voltage difference and current of the idealized voltmeter and the idealized ammeter. Here we have an EMF source with EMF equals 12V and internal resistance R equals 2 ohms connected to a 4 ohms resistor. What are the voltmeter and ammeter readings? First we determine the current reading using the equation 21. And we have the current equal to 2 amperes. We then use this value to solve for voltage difference, and we can do this in two ways. The first one is determining at points N B prime. Using equation 17 we have the value of the voltage equal to 8 volt. Second way of measuring it is done by using points A and B. We do this by using equation 20 since we are determining the voltage using the battery. So we have the value of 8 volts also. Potential changes around a circuit. The potential energy changes as it moves around the circuit would result in a net change of 0. Here we observe the decrease of the initial EMF voltage of 12 volts as its current goes through each resistor. The internal resistance of the battery brings down the voltage by 4 volts. Then the second resistor further reduces the voltage by 8 volts. Here we see the flow of current moving from a high potential back to the low potential, or for this case from the positive end of the battery to the negative end. The battery will then push back by the non-electrostatic force, creating an electric potential difference again and continuing the flow. Here we have a box which represents a device such as a battery or resistors. The current flows from a point of high potential towards the low potential. The work at point A and point B are denoted as V sub A and V sub B. The electric field does work on a charge here and it is written as equation 22. The work equation can be expressed also in terms of the negative change of electric potential energy as shown in equation 23. For this case, the charge is positive and the electric potential shows that the change is also a positive, so that means the change in electric potential energy is also positive. This suggests that as the charge moves from high to low electric potential, its electric potential energy is decreasing, since for the change in electric potential energy to be positive, then the electric potential energy at point B is less than that at point A. To obtain an expression for power, we recall the current expression, which is given as the rate of change of charges over time, and we have equation 24. From equation 23 as a derivative form we have here. Substituting equation 24 to the work function. We then divide both sides by dt to get an expression for power, which is given as equation 25. Applying Ohm's law, we can express power in equation 26 and equation 27. Power is the rate of energy transfer done by the system. The unit of power is still in watts. Here we have an EMF source connected to a device. We write an expression for the power due to the EMF source. We recall the expression of power, which is given in equation 25. Substituting the electric potential difference, we have the power expression for an EMF source as shown in equation 28. The first term is the power related to the non-electrostatic force that pushes the charge to move from low to high electric potential. The second term is the rate of loss of energy due to internal resistance of the source. Suppose we are charging the battery by connecting it to a device with higher EMF, such as an alternator in automobiles. We see that the current now flows in the opposite direction since the alternator has a much higher push. So the voltage and power now are shown in equation 29 and 30. This is now being done on by the devices, and there is conversion from an electrical energy by the alternator to a non-electrical energy. The power here is not a rate loss but a power input. Sample problem. Here we have a circuit and find the rate of energy conversion from chemical to electrical and energy dissipation in the battery. The given values are shown on the figure. We recall the expression for the power output for EMF sources shown in equation 28. The first term is related to the rate of energy of conversion from chemical to electrical energy, so if we calculate this we have 24 watts. The second term is the energy dissipated or lost due to the internal resistance of the EMF source, and it is 8 watts. The battery's net power is just the sum of the two using equation 28, and it is 16 watts. Suppose we replace the resistor to 8 ohms, find the electrical power dissipated in the resistor. First we must identify the new current by using equation 21. And it is 1.2 amperes. The voltage for the resistor is calculated using Ohm's law and it is 9.6 volts. The electrical power dissipated in the resistor is about 12 watts. You can also solve this using a different equation here and still it is about 12 watts. That is it for now and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.